He graduated this past year. Anyway, Carson was all about, he was the practicum, we did the micro hydro. Carson was all about the geothermal. I mean, I think he really wants to go and work the wind farms. You know, he's young, got a lot of energy, a lot of spunk, but I think one of his goals in life is to work the geothermals. I think it'd be cool. In fact, something tells me, I just keep thinking, I don't know, but that ultimately we will have sufficient knowledge, mapping capabilities of seismic plates, and that we will be able to avoid earthquakes. I mean, I think we'll be able to go down there and just like, preventing further cavities in your teeth by filling the holes, we'll be able to prevent earthquakes eventually. And at the same time, get down deep enough that you're pulling off some major heat too, that you're actually extracting geothermal and I don't know if we'll get to the point where we've got a national distributed thermal heating system, but that's already happening pretty big time in a lot of cities in Europe, this distributed heating. And we used to read a paper in 102 by a engineer out of Duke University that did some pretty neat modeling on it, but I think that's where we need to go and where we will go. And in fact, tomorrow, when I'm giving my talk to the Missoula Federal Credit Union, one of the things that I would like my house to do would be able to share my heat with my neighbors. So if you got extra heat, coming off a compost pile, or even coming out of the wastewater from your shower or your dishwasher. If you go out and look at the sewer vents, a lot of times there's no snow on top of those guys. They're just warm enough with all the waste heat coming out of houses to keep that. So what I'd love to do would be able to cap that, send the hot gases like up the hill. And Missoula's a perfect place. We got all this neat topography. Send the hot gases up the hill to the folks on the hill. Send the warm water down to the folks in town. They're sort of sharing their nice toasty, warm, stinky waste streams. But put it to use in some way, rather than just heating the environment. So, okay.
Yeah, a friend of mine, they took their dryer vent and they attached it to a bucket, a 5-gallon bucket.
Yeah.
And filled it halfway with water, and then they poked holes
Yeah.
above the water level. So the lint itself goes into
Sure.
the water and the hot air comes out.
Yeah, I've seen those. Is it an electric dryer or a gas dryer?
Electric.
Yeah, I was going to do it with my gas dryer, and then realize that's a lot of CO2. If I want to, if I had a really buff greenhouse going that could absorb all that CO2, I might have done it. But yeah, with the gas dryer, not advisable. Yeah, unless your house is really drafty. Well, but if it's drafty, then why bother with the heat? I don't know. It's a good thermodynamics problem. One for the final. Design but that would be an example of a low enthalpy system, where you're just sort of getting that waste heat, low enthalpy. Okay. Yeah. So here's something. I'm just going to read this little geothermal waters. We had a question about this in 101. It says hot water tends to be more reactive than cold water. So geothermal waters can often contain around 1% dissolved solids. Kind of makes sense, right? All the little ping pong ball water molecules are able to suspend more solids. Typically these will be carbonates, sulfates, and chlorides. We saw those in the diagram. A little bit of dissolved silica. So they're called brines. Sometimes gases are there, and they just need to be dealt with. It says with correct design, these contaminants can all be handled and disposed of without either operational or environmental difficulty. Disposed of is getting to be a little bit of a loaded word. I think a couple of, Sean, you might have heard this earlier today, but a gentleman I met with yesterday has a zero waste facility going in Vancouver, Canada, and those guys pull off a lot of gold each year. I mean, it's kind of everywhere. And so once you sort of commit to absorbing a waste stream, like literally, who knows what's in it, but also a little bit of everything. So some of it has more value than others. Okay. There's also, I love the historical perspective here. I'm just, hot, dry rocks. It was thought initially that deep basement rocks would indeed be dry, so the term hot, dry rock was coined around 1970 to describe the heat stored in impermeable. It says, though, more recently, it's been recognized that few, if any, rocks are actually dry, and there's now a general acceptance of the term enhanced or engineered geothermal systems to categorize projects aimed at extracting dry heat. But from my perspective, and from what we know about heat transfer, if you have moisture in there, your heat transfer is generally going to be better. Because the water molecules themselves are actually transferring the heat rather than relying on air to do it, and air is not as good. This is another one to keep in mind. It says drilling is expensive. The costs rise exponentially with depth. I think having studied Summary 3, we know what that means. The deeper you drill, the more expensive it gets per meter to drill. So it also says, but to get to high thermal gradients, you got to go deep. So again, there's your kind of cost benefit. I haven't read your Summary 4s yet, but that's something, obviously to consider. It's much easier to go after something that's local rather than having to drill after it. Okay, next one, and we talked about this a little bit, technologies for exploiting high enthalpy steam fields. So these technologies are going to look a lot like the coal-fired power plants and the gas plants that we looked at in 101. But let's just take a look here. So dry steam power plant. So here's the geothermal zone. You've got that pressure that's already there. So just think deep water horizon, right? Instead of oil spewing up into this pipe, it's steam coming up through the pipe just from the Earth's pressure. That goes through a turbine, makes electricity. Now the steam is then sent through a condenser. And how does it get cold? Well, it's sitting here in this cooling tower. The hot well on this side, as this air, well, there's enough hot on this side. It's still not as much enthalpy as on the steam side, but you have to do something with the water, and so it's heading back down into the hot well. There's no fluid exchange really between these two sides and the condenser, just heat exchange. So all of this is just water, and then again, just the fluid itself is lower. And I'm not really sure why they decided to make this water red here, because it's already kind of condensed and passed through, but anyway, there it is. Okay. Here's another one. So if instead of having steam coming out of the ground, you've got brine, but it's still hot enough that all of the, so think of this as more like a geyser, right? So you've got some fluids that's re-injected, and the steam operates just as before. This is called the binary cycle. So the fluid itself, the steam itself, never goes through the technology. It's just used as a heat exchanger. Everything else is identical. This one's a double flash point power plant. And if you remember when we were looking in 101, when we were looking at steam turbine generation, you might have several turbines in series. Some are going to work at high pressure, some at low pressure, and that's really all this is. It's just milking a little bit more out of. So your first stage is high pressure, second stage is low pressure. They both spin, make electricity. Everything else is basically the same. So just different strategies for pulling energy out depending on what the geothermal source looks like. And how much money you got. And they're all described. Okay, so this is technology for direct use of geothermal energy. I think I might have mentioned that my parents, when they built a house, they put a little heat pump out in their lake, so they're just sort of, directly using, I guess we call it, aquathermal or liminal thermal, what have you, from being taken from a lake. But in this case, again, you've just got hot water, not boiling, not steam coming out in a loop. So this can be sometimes just called a pump and dump system. In this case, they do have a heat exchanger. They've got a lot of surface area. The water inside the building or the structure, if the heat exchanger is designed well, will get most of that temperature, so 60, just down to 55. Here's your 2,000 apartments, underfloor heating. At 35C, if you've got your heat pumps running, you can get refrigeration from that in just a normal refrigeration cycle, as well as radiator heating. So obviously electricity goes in here, but you're doing refrigeration. 10C, it's getting down there. I mean, I think most refrigerators want to run around 4 degrees or so Celsius, but so you could actually have a refrigeration system right there, and then back through the cycle. So you're not making electricity like we were in those previous examples. Okay, so that's 9.4. Ground source heat pumps. This is the growth worldwide of different direct geothermal applications. The area of the circle is proportional to the capacity. So as that circle gets bigger, the capacity gets larger. So we're at 8.7, 15.1. We're almost doubling every 5 years. And thinking back to that our chapter on economics, if I were looking at this as an investment banker, something that doubles every 5 years, yeah, I'd put my money there. So, and it sounds like it's exactly what Bill Gates and the gang are doing. They're not going to necessarily wait around for the governments to fuss and fart over their policies and all that. Like, hey, we got a lot of money. We know there's a lot of ideas. Let's fund them and just economically force the fossil fuel companies out of business. So. Yeah, it's happening. I'm pretty stoked. I'm pumped.
Hydrofusion reactor?
What's that one? Hydrofusion?
Yeah, Time magazine had an article in their November issue about a hydrofusion reactor. They actually work.
Okay.
Ashley's got it right now.
Oh, really?
A copy of it.
Oh, okay. That's cool. Yeah, that's a pretty volatile research topic too. I think MIT closed its fusion reactor a few years ago, but I know there's a few still up and running. Yeah.
Microsoft and Google and all them financing.
Mm-hmm. Yeah. And what I think we're going to find, and in fact, when we get to our next chapter, chapter 10, there will be a lot of integration that goes on. It's not just going to be a one-size-fits-all. There's not going to be one answer. It's going to be a lot of integration of these technologies. Okay, now if you're fortunate enough to take Jonathan Bowe's NRGY 246, you'll actually get to do some experiments like this. A few years ago, we just bought a few remote temperature sensors, been having all the students in 246 dig their own little wells, just 6 feet or so, something dig by hand, and track temperature as a function of time of day and over several weeks. And what this figure is showing is that well, first of all, that as we go deeper, the temperature becomes greater, right? So we're looking at, well, if we just look up here at 20 meters, the temperature is about 8 degrees. When we get down here to 100 meters, we're closer to 11. So, 3 degrees difference. What they're showing here is that early on, when the well was first dug, it was relatively, so this is 1986, relatively undisturbed. This is more or less your air temperature up here, relatively cold. Let's do the conversion really quick. I want to go from Celsius to Fahrenheit. 52 F to C. Okay, so 52 Fahrenheit is 11 degrees Celsius. I keep 52 in my head as like that's what ground temperature is. So if we look, okay, there it is, right about there, 11 degrees. So what they're showing is initially you've got near the surface relatively cold temperatures. Once the drill has gone in, here's 1987, and heat is actually flowing. These are the temperatures that are basically coming back out of the system. So if you look right here, it's the geothermal heat exchanger. One side goes down, the other side goes up. That accounts for this big flip-flop at the top, because what you're looking at is sort of waste heat from the house heading back down. So 16 Celsius, let's do that, 16 C to F, there's your 60 degrees in the house, warmer, more, well, this would be used for cooling, and a 60 degree water coming back out of a 80 or 90 degree house is obviously still doing some cooling, sending some of that thermal energy back down into the earth. And I think what they're also trying to show is that it's relatively stable. It hasn't changed much. It's not like drilling a hole has caused this to drift, where the whole thing is sort of moving to the right. In fact, it looks like it's kind of gone the opposite way. Like in 87, everything was slightly hotter and relatively cooler. So not much change. So this is an example of a sustainable geothermal loop, right? It's not cooking itself or freezing itself. Looking at depth as a function of time of year. A little hot, hottest in July. It's surprising it's that colder in April. The point is, though, once you get deep enough, the temperature is relatively constant. Okay. So these are all relatively passive, right? You drill a hole, you put some pipe down there, you set it up. The next topic, I'm looking at page 438, and these are called enhanced or geothermal, enhanced or engineered geothermal systems. Let me get to the next set of lectures, next set of slides. Strange. Somebody stole my second half here. Chapter 9, Part 1, Geothermal. Let me take a look for it. 1 second, guys. Sorry. Chapter 9. I found that these searches get faster and faster. Okay, that is very strange. I do not have part 2 of this chapter. Well, it's okay. What I'm looking at right now is figure 9.2, so if you can follow along in the book. If you guys need to open some blinds, it's getting a little dark in here, you're more than welcome to. What we're looking at is heat in place, and this is in 10 to the 18th joules. This is pretty impressive. So I'm just going to read through this. It says, heat exists everywhere, and the amount of energy stored within accessible drilling depths, say down to 7,000 meters, and that's what the maximum figure is there in figure 912, where temperatures of greater than 200 Celsius would be widespread, is colossal. So the deeper you go, the more there is. Cooling 1 cubic kilometer of rock, might seem pretty big, but from the Earth's standpoint, still kind of small. Cooling 1 cubic kilometer of rock, which is about the scale of a geothermal reservoir, by 1 degree Celsius. So we're not even like cooling it that much. It's going down 1 degree Celsius. Will provide the energy equivalent of 70,000 tons of coal. Not too shabby. So there's no shortage of geothermal energy. Just to put this in context, and I love these big numbers, a report prepared by the Massachusetts Institute of Technology for the U.S. Department of Energy in 2006 calculated the heat in place at various depths in the continental USA, excluding Alaska, Hawaii, and our favorite local caldera, Yellowstone National Park. Love it. The estimate was 13 million exajoules. By comparison, the total annual consumption of the U.S. is about 100 exajoules, even though the only small fraction is likely to develop. So let's just do those numbers, though, in terms of years. So let's just say we're going to quit coal tomorrow, quit natural gas, and just go straight up geothermal. So, and again, this is sort of making the assumption that the entire continental U.S. down to 7 kilometers is economically and technologically exploitable, which it's not. No one's going to set up shop downtown Manhattan and start drilling in the center of the earth. But let's just look at the numbers. So 13 times 10 to the 6th exajoules. So we're looking at is 13 times 10 to the 24th. Okay, now, how many years is that? So if we've got 13 times 10 to the 6th exajoules, and then we've got, that's pretty accurate. 100 exajoules, remember the global budget is 500 exajoules. The United States consumes about 1/5 of the planet's energy, so pretty easy math, 100. So 100 is 10 squared exajoules. Let's get our units correct, per year. Equals, so exajoules cancel, 10 to the 6th becomes 10 to the 4th, so 13 times 10 to the 4th. Years comes up top, so 1, 3, 1, 2, 3, 4, comma. Okay, I can deal with that. There's your grandchildren's grandchildren's thermal source. Yeah. You know, by then we'll have our solar panels and wind turbines figured out too, and
Right.
yeah, so, you know, to pump our geothermal energy.
So the values in this table are per cubic kilometer?
In figure 12.9,
Yeah.
this is total. No, this is the total. This is not per cubic kilometer. Yeah, so, yeah, right, so the way, yeah, it is. So the way to think about this is, you know, here's the, there's the US, right, something like that. And then what we're looking at is, that's not too bad. Little USA, what are they called? Cookies, gingerbread cookie? No, so we're looking at 7,000 meters, 7 kilometers. You know, it's not, I mean, it might seem kind of deep, but that's like from here to my house. It's not that deep. You know, it means it's from here to Mount Jumbo. You can see it practically. And what's the area? Let's see. Let's just check out the area of the United States. Come on, Wikipedia. Gave you my $3. It's usually right over here in the continental U.S. Contiguous? What's that? Why is this, it's kind of weird. Why is it coming up like that? It's kind of a funky looking Micronesia. What? Yeah, it's just, I bet Google can find it quicker than Wikipedia can.
And they'll just send you to the Wikipedia.
I know. United States, Wikipedia, there it is. There's my gingerbread cookie too. It's funny. So if we scroll down, there we have it, government, vice president, area, there we go. 10 million square kilometers. So, I mean, we're looking, so that energy is in a volume of 100 million square kilometers. And it's more or less, now it doesn't say, I mean, I have not read the paper, but I'm assuming that means bringing that entire 100 million cubic kilometers basically to air temperature. So, I'm sure there would be some environmental consequences there as well. There always is. So, but nevertheless, some folks at MIT sat down and did the math.
They only got an 80% on that second.
They did, yeah. They probably only got a B on their homework. Yeah. Love it.
They used only Wikipedia, not.
That's right. Yeah. Oh, shoot.
It's scary the things that Google comes up with though sometimes.
Well, you know, it's. I mean, what is Google if not just human knowledge? You know.
Now Google will respond to you
Oh, really?
through your cell phone.
Oh.
Talking to my brother.
Oh, you mean with the app?
Like through a Siri, like through a Siri question type thing?
He
Yeah.
asked Google, he was like, how long does it take to cook prime rib at 200 degrees?
Okay.
So Google gave him his answer. Well, about an hour goes by, and he goes, well, and his phone's just sitting there like this. Didn't even touch it, and he goes, well, the prime rib's been in there about an hour. I wonder how much longer it got. His phone responded and told him how much more time he had. Google responded to him.
Did he have a Google probe in his prime rib, or just kind of?
Yeah.
Yeah.
That's where the data is.
Our prime rib was perfect. I can't complain.
Well, I've already seen in a lot of my lectures that YouTube is doing voice to text, and I am positive. I mean, all those guys at YouTube got to be doing something. I mean, I know where artificial intelligence was 25 years ago. I'm sure it's way beyond that. I'm thinking there's a big old YouTube brain sitting out there just ingesting the stuff coming out of my mouth, figuring out whether it's worth anything or not. Yeah, it's fun. Okay, I don't have figures for the rest of the chapter. I'll see if I can get those from the publishers before Thursday, but there's still plenty of neat stuff in this chapter. I love this book. Probably said that before. Okay, I'm going to email my pals and see if I can't get that second zip file.